First of all, who am I? Associate Professor Simon Michaux of the Geological Survey of Finland. I was educated in Australia, basic degree physics and geology, and then some postgraduate work in open pit optimization and mining geostatistics, PhD in blasting, in mining, and then I was in research and development in the mining industry for 18 years. Left the private research and joined the private sector, supporting feasibility studies. I left that and the mining industry at large, came to Europe in 2015 to learn industrial recycling. While here, I came across the circular economy for the first time, and I was trying to develop a career in recycling. And then now I've moved to Finland to do industrial mineral intelligence and industrial data mapping, and I'm attached to a pilot scale process plant. Okay, that's me. So do I just share screen and get into it? Yeah? Okay, all right, sharing screen. Okay, so can you see that okay?
It's there, yes.
And we'll go to presentation mode. So this is a lightning fast summary of 2 pieces of work, both of which are being published in peer-reviewed journals as we speak. It's been through the first round of peer review, and it's now going out to external peer review, and full calculation of what you're about to see is about to drop. So I'm going to look at the challenges and bottlenecks for the green transition. Now, what I'm trying to suggest here is no more chit-chat. I'm not trying to describe whether we should do the green transition or not. That's given. We are now going to do it. These are the logistics and mechanics of how we do it. First of all, why was this work done? When I first came to Europe in 2015, it blew me away. I used to sit in the European Commission Central Building listening to these meetings about circular economy H 2020, and there was no credible feasibility plan to phase out fossil fuels in any form anywhere in the world. There was just a lack of hard numbers. Everyone used to talk in platitudes, what we used to call arm waving. Now, the problem with arm waving is it gets people fired. Companies lose projects. So we need the numbers. There was very little awareness of the current dependency on fossil fuels. Fossil fuel energy was abundant. It just happened in the background. It's like the oxygen we breathe. There was no discussion of our dependency on minerals, yet we consume minerals and metals on a yearly basis. The whole commodity sector was seen to be considered a market phenomenon. It was boiled down to an economic issue. It was price fixed everything. It wasn't seen as a finite series of natural resources that had engineering bottlenecks and extraction. Promises were being made on what industry could deliver in all sectors: mining, smelting, manufacturing. It was the most amazing amount of bullshit that I ever heard about what they thought the future was going to be. And these guys were laying down the hammer of how we were going to live. So the reason I just to show this to my management, at some point in the near future, European captains of industry would turn to the European Geological Surveys, GTK in particular, and ask this question: why didn't you tell us about this very obvious mineral shortfall? When management understood this, that yes, actually that was them. Society is depending on them to actually pass judgment on this if there is a problem. So the whole of GTK is now behind me on this, and multiple people are now working on this in different areas. Before we get to that, let's look at oil. What are we replacing? So this is total liquids production. And total liquids is everything from oil, biofuel, and other sources like gas, turning to make gasoline. We had a localized peak in November 2018, and there was a thought that that could have been peak oil. Then we had COVID, but you can see we've recovered, and the rate of the recovery suggests that, well, maybe we'll get back to business as normal, and the whole idea of peak oil's over now. Let's unpack that. So the blue, this was put together by Art Berman of Labyrinth Consulting. And as far as I know, he's the first one in the world to actually highlight this. The blue is oil. And so there's our localized peak oil. And oil is in fact declining. I think that probably is peak oil. However, What we mean by peak oil is what gets brought to the market in terms of gasoline. Biofuels now take a massive hit, and about 40% of all gasoline that comes out of the United States is now being derived from gas. So the gas industry is now supplanting the oil industry. And that's really bad news because it's not efficient, it's not calorifically sensible, and we're building in a deep inefficiency into the oil market that has spent decades becoming very efficient, and it'll get worse over time. So when the gas industry can no longer deliver to actually hold the oil industry together in addition to what it has to do industrially, we will see a very steep decline. So what this shows is fossil fuels are done. You get your climate change spectrum of issues, but now you've got resource depletion. Whether peak oil really was 2018 or it's in a couple of years' time doesn't matter, because the scale of the problem will require decades of work to phase oil out. We are looking at the end of growth-based economics. So, getting rid of fossil fuels. So far, all strategic decisions that's been adopted by literally everyone have focused on carbon emissions. We're trying to get rid of carbon emissions, and it's been associated with climate change targets. At no time, or not that I've found, have they been looking at finite resources, either the ones we're about to get rid of or the ones we think we're going to use to replace them. It's simply not part of the thinking. So I developed a system a way of communicating what it was I was seeing. How do I put the information that I've been collecting in the Australian mining industry since 2008 that would be in a form that couldn't be ignored? And so what I've done is develop what I call a bottom-up approach. Instead of projecting what might happen next year or the year after, I've looked at what would happen if we were to replace the system around us now. All cars, all trucks are now replaced with some kind of non-fossil fuel system. All electrical power generation is non-fossil fuel. Now, the people who control our society, this is the banking sector, geared on growth. They're also geared on the idea that we get more complexity. And this is a very simple matter, is that the green transition will come in and make the internal combustion engine technology obsolete, and it'll just be phased out economically. And they're completely untethered from reality there. So asking basic questions like how big is the existing transport fleet had not happened for a global sense. They had it for the United States and for Europe and for China, but no one had put it together for the whole world. There was no question about how much metal we would need or what kinds. And so I've replaced the whole system, and now we're going to work back from there, follow the existing paradigm. I'm going to use predictions from the IEA in terms of market prediction for chemistries and for the future, and I'm going to roll out a plan of what they think is going to happen. There are things we can do instead, but this is what the bankers believe will happen. So here is the map. So I'm going to show a map of the way things were in 2018, and then we're going to look at what we would need to do to actually transition out. So there's three basic fossil fuels: oil, gas, and coal. They're the main applications. The self-propelled transport grid is split up by that. Most studies I had looked at, especially around 2017, looked at passenger cars only. They did not talk about trucks. They're starting to now. They did not talk about rail in a engineering context. They did not talk about aircraft or maritime shipping. Yet all of that we are dependent upon. So I put forward the idea that all short-range vehicles will be electric vehicles due to the mass of the battery versus the mass of the hydrogen fuel tank. But to do that, we need 65.19 terawatt hours of batteries. Now that, all other studies I've seen have gigawatt hours of batteries required. I've got terawatt hours. It's 1,000 times. What's happened is the World Economic Forum put out a report in 2019 that estimated the size of the global transport fleet, that when you actually unpack their numbers and back calculate, they have seriously underestimated the size of the global transport fleet. They seem to have about 240 million vehicles, where I've got 1.4 billion. All long-range vehicles should be hydrogen fuel cells. The tank will last longer, energy storage, what have you. However, you've got to make the energy. Aircraft, what made sense was to take it to biofuel, but we can't actually take too much more from the environment sustainably. So we have to have an intelligent conversation about what's sustainable and what's needed. It was possible to make plastics out of bioplastics, but again, we're now tapping into the natural environment. That's actually another piece of work that has to be done. What is actually sustainable to be harvested? Because we're over our skis in many respects on what we do take from the environment. Petrochemical fertilizers had no viable replacement, and the recommendation is there we go small scale organic. So electrical power, oil, gas, and coal, heating usually done with gas, and the coal industry, the manufacturing of steel, use coal 70% of the time. So if that was all electric arc, what would that look like? Put that all together, and that's the amount of power we need to phase all that out. To charge the batteries, we need about 4,500 terawatt hours for the year, but to make the hydrogen, we need 12,800 terawatt hours a year. Now, the electric vehicle fleet is 1.39 billion vehicles, but the hydrogen fuel cell fleet is 29 million. So the H cell fleet is much smaller, but does most of the useful work, and now needs almost 3 times the power to actually function, about 2.5 times the power. So what that means is the hydrogen economy must take precedence over the electric vehicle fleet in terms of importance of what it does for society. Put all that together and assume 10% loss in transmission between the point of application and the point of generation. We need 37,289 terawatt hours a year on top of our existing non-fossil fuel systems. We're not allowed to use fossil fuel systems, so there's our options. The elephant in the room is wind and solar is highly unstable, and it needs a buffer. And so I've estimated we need something like 2,000 terawatt hours of buffer, and that buffer, according to government policy documents, they think it's going to be batteries, because there are problems with others. I'm going to talk a little bit more about that later, about why that number is so large. That's the elephant in the room, though. Okay, so here are the numbers graphically. On the left, we've got the global power generation in 2018. So it was 26,614 terawatt hours for the calendar year. Excuse me. Down the bottom are the bits in color. They're the parts we can keep. All the oil, gas, and coal we've got to phase out. On the right, we've got the green column. This is what we need to phase in. So we need 37,289 terawatt hours in addition to what we have now. That is larger than the existing power system, right? And the jobs are charge the batteries, make the hydrogen, electrical power generation, heat the buildings, and coal-fired steel manufacture across the top. So we wish to construct an electrical system that's much larger than the existing power grid, using energy that's more expensive and simply not as effective as what we have now. And it doesn't include everything. These numbers are too small. They don't include what was used by industry for manufacture. For example, to manufacture a solar panel, you've got to take silica to make silicon wafer. You've got to heat it to 2,200 degrees Celsius. And they use coking coal to do that almost always in China. Take coal away. How are you going to generate that heat to that temperature? You can use biofuels, you can use hydrogen, and you can use electric arc. All of those options are doable in a small scale. Now scale it up to replace the amount of coal being consumed. Right, that number there should be much higher. I was not able to get consistent numbers across the whole industry, so I didn't include it. So the snapshot is current plans are not large enough in scope. We just don't seem to understand the nature of the plan before us. And the phase out fossil fuels is larger than we thought. We should have started this 30, 40 years ago. So we need 37,000 terawatts. Now, if we take an IEA prediction of the energy mix of 2015 that was released in ARENA 2022, and then I've added a few of my own insights, and I've taken away the gas industry entirely. That's all in the paper that's coming. We're talking about 607,000 new average-sized power stations across in the global system. The existing power plant fleet is 46,000. So there's more than 10 times the rate there. So to take out a given coal-fired power station, how many solar panel arrays do you need? How many wind turbines do you need? So according to that balance, they're the numbers. That's what we're talking about. And wind and solar now represent about 70% of the energy mix, right? And that's why the power buffer storage is so massive. It's quite, so the wind and solar need a massive power buffer. So let's talk about that. This is Europe power production in 2021. What happens here is each nation grid shares power with everyone else. No one nation makes just enough power. They either make too much or too little, and they share it. The reason they share it is supply and demand must match to a millionth of a second. We must have exactly the same power meeting the supply versus demand, and the only way we can do that is through power sharing. We have not done standalone systems that require power buffers yet. So all non-fossil fuel power systems, like wind, for example, in Denmark, at the moment are balanced with power being supplied by external networks, usually fossil fuel. Thing that the engineering industry simply hasn't done yet. They just haven't done it. We haven't actually got to the point where we're balancing large systems in a standalone fashion. But if we're talking 70% of the grid is now wind and solar, now we have to. A lot of my work is criticized on social. In particular, the main complaint is my selection of power buffer for 28 days is way too much. And the reason they actually give for that is the outcomes of a study done by Net Zero America, which is actually released by Princeton University. They recommend 5 to 7 hours. How do they get that? So here's how they get that. The black line there is demand load, and supply has got to meet that. Sometimes supply exceeds demand, and sometimes it's below demand. When it exceeds demand, they will store it, and then they'll release it when supply is below demand, as per that diagram. The problem is they're only looking at a day-to-day fluctuations between supply and demand. They're not looking at the long-term variations. For example, the difference between summer and winter. Watch this. Here is solar radiance in Germany, 2015. You may notice, this is not the same as power production. Solar radiance leads to the ability for solar panels to produce power, sun hours. So this is not rocket science, but in summer, you get more sun than winter. So if this now represents 33% of the global energy mix, and it has to be internally self-sufficient because of its size, it has to deliver power evenly across the year. So let's say we'll pick the halfway point, and we're going to have that solar radiance, which is now going to supply all systems from that point on. For 6 months of the year, excess storage will have to be collected. And then for the other 6 months of the year, that excess needs to be released slowly. So what that means is the power buffer would need to collect excess power over 6 months, store it for something like 6 months, and then release it slowly over 6 months after that. That red square is the equivalent of 28 days or 1 month. The other reference I found was 48 hours plus 10%. So I'm going to show you the numbers associated with that. So that's 48 hours plus 10%. I would put to you that both of those numbers are actually too small. And the answer is we don't try and find more power buffer. We actually change our electrical technology that needs the buffer in the first place. So the answer is actually technology innovation, not more resources. But I digress. Here is a case study of concentrated solar power in the month of June, which is summer, and the month of November, which is winter. Now, if this was to provide an even 670 megawatts of power in a self-sufficient fashion, for the month of November alone, it would require 16.2 days of storage buffer, and that would have to be collected in summer and then kept for a period of time. This is the long-term problems, long-term variations of wind or solar. Now that brings us to wind. The UK Parliament did a study of wind, and they found that power production was so erratic it couldn't be predicted. What didn't help was they got hit by a couple of big storms, and that really, during the assessment period, that really threw a spanner in the works. So here is the following year. from that study. That's what a normal wind meterage looks like. Now, let's say that chart now represents 1/3 of the total energy mix. It has to be smoothed out and it has to be self-sufficient. Here is data for Sweden, Denmark, UK, France, and Germany all put together. Now, what this shows is when you're seeing, look at these peaks. You're seeing quite a large peak, and then you have a trough for a couple of days. When you see a peak in one region, you often see it in all regions at once. So we're not in a position where we can balance power from one wind power system to another. It doesn't seem to work out that way. Now, some of these variations in this data set were up to 48%. The size of that peak is dictating the size of the power buffer needed. Any information I collected from the Global Energy Observatory, across the calendar year of 2018, solar PV produced power 11.4% of the time, and wind was operating at 24.9% of the time. So we're going to have to build out many of these operations, and they're going to be standing idle for long periods of time, not producing power. Like a coal-fired power stations generally has an availability of about 90%, right? And so you need many solar panels to replace a single coal-fired power station. That's a reality. So here is the energy split that is being used, where wind and solar actually have the lion's share. And so now we're going to look at, in the literature, so now we need a power buffer with wind and solar. In the literature, there were two references that I picked as what I thought were bookends. One was 48 hours plus 10%. That study looked at passenger cars only, and it was 2012. The second one looked at 1 month buffer for the whole system. So I picked what I thought was a relatively conservative 28 days for wind and solar only. Now, 76% of the new power grid, if we phase out fossil fuels, is actually larger than our existing power grid. Now, that's the size of this thing. And so that's how we get to 2,192 terawatt hours, or the lower level is 172 hours. Now, I'm going to take those numbers and I'm going to use them to calculate the amount of metal needed. So here is the number of technology units to replace the fossil fuel system that you've got around us now. Electric vehicles, there's your 1.39 billion vehicles. There's the hydrogen fuel cells. Many fewer vehicles, but they do most of the work. There's our wind turbines, 70% onshore, 30% offshore, as per what the IEA recommends. Solar panels, assuming that all solar panels are a 450 watt commercial grade system, and there's a stationary buffer down the bottom. Now, all of these units are to replace a fossil fuel technology system. They harvest renewable energy like sunshine and wind, right? But they themselves are not renewable. A wind turbine wears out after about 20 years. A solar panel wears out after 20 years, and they have to be decommissioned and replaced. So they're not renewable, they're actually replaceable in their current form. And each one's manufactured from metals and materials. Less than 1% of the vehicle fleet in 2018 was ICV. I think we're a little over 1% now, right? And energy accounted for about 4% of primary energy. So the non-fossil fuel system does not exist yet. It hasn't been constructed. And as it hasn't been constructed, we can't recycle it. So the first generation at least has to come from the mining of minerals. And so minerals are the new oil. And the message here is, if the environmental movement does not join hands with the mining industry and become allies, the green transition will not happen. And that is actually something I've had to explain to quite a few of the activist groups, and they really didn't like that. But this is the reality of what we're looking at. So the second part of the work was, how much metal do we need? So an IEA report, Critical Minerals in 2021, had a whole series of examples that actually looked at what metal is in each unit. These are wind turbines. There's 4 different models that dominate the market. We've got an estimate of market share, how big that market share is, and what metals in each one. We've also got an estimate of what's in each of the dominant battery chemistries. I also established what was in solid-state batteries and vanadium redox batteries. And that got us to this point here. So bottom left-hand corner, we've got light-duty vehicles and heavy-duty vehicles if they were electric vehicles. In 2040, there's an estimate of market share. What chemistries would have the market share? And so we could then take that information and then say, for this study, we're going to use these splits. And that's for power storage. And because we also happen to know a number of vehicles we need, the amount of battery capacity we need, the number of batteries, and market share, and we've projected that onto, by each chemistry, we know what's in each metal. So we can now list, for a global transformation, how much metal we need by chemistry, and then sum it all up to the edge on the right-hand side. Now, this study has about 70 tables of data, and it's 150 pages to describe. It's about to be published. You're seeing the very tip of the spear. Here is these numbers graphically. Okay, that's a log scale. So at the top, there's 10,000 million tons, and down the bottom, there's 0.1 million tons. The red, this is by metal, copper, nickel, lithium, etc. The red is all units put together, how many EVs, their batteries, wind turbines, solar panels, new nuclear power plants, etc., 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 assuming a 28-day buffer. That's the red. The blue is assuming a 48-hour plus 10% buffer. The yellow is reported mineral reserves. And the black is global production in the year 2019. 2019 is the last year of sensible data. After that, we've got the COVID pandemic supply disruptions. So looking at this, remember, this is just for the first generation of stuff, all of which wears out after between 8 and 20 years. And even if you wind it back to, say, 30 or 40 years, you've then got to replace it and do it all again. And that puts on the recycling industry. They've got their own problems. The biggest one is logistics of actually getting the right residue into the right plant. So this is a mining problem, and you're looking at the mining industry's ability to deliver. Sensible conclusion you could draw, for example, is why don't you just make batteries out of something else other than lithium ion? That is true. That is not what the European Commission is thinking. But let's say you do. You make them out of zinc or fluoride or sodium or silica. You're still going to need copper to electrify everything. Here is rare earths. This is actually driving a lot of the electrical technology, especially wind turbines, solar panels, and the current production rates. There's literally several thousand years of production to keep up with that. So usually what happens is people would say, well, that's just reserves. Price will go up and more resources will be classed as reserves. A reserve is an economic feasibility study. So, all right, the red is the amount of metal we need. The yellow is reported reserves. The green is reported resources on land. The purple is actually reported resources in the sea. So you sum them all together. So the red is the metal we need. The column next to it is the entire metal that we know of in the system we call planet Earth. Remembering that has to be replaced in 20 years somehow. Now I'm going to make the point. I'm trying to make the point here that we cannot continue like this. This is copper production. Copper production from 2020 back to 4000 BC, we mined around 700 million tons throughout history. To keep up with demand as it is now, not including the Green Revolution, we will do the same thing in the next 22 years. Reserves at the moment are 880 million tons, which is about 30 years. The current state of the copper industry is they are now falling behind, and we may have actually passed peak copper. On top of this, we want 4.7 billion tons to manufacture the first generation of non-fossil fuel technology. That's 6.7 times the historical quantity. And they think they're going to do that in a couple of decades. I would propose that a radically different plan is required. Okay, so mining production is not enough, and we need to do something else. What is it? Our current plans for phasing out fossil fuels are simply not good enough. They just don't reflect reality. The size of the task has been underestimated. These are not technology problems. These are logistical scale-up problems. Battery chemistries other than lithium ion will be developed, whether we like it or not. That is not the thinking of our strategic planners at the moment. Renewable systems may not have a strong enough energy return on energy invested ratio to replace fossil fuels in their current form. This may not be strong enough to replace fossil fuels. And so the hopes for future technology breakthrough to somehow deliver more commodity resources don't seem to consider the nature of what mineral resources that are left. And the current system has no concept of its dependency on minerals and does not consider long-term concepts like continuous growth and production against finite resources. The smart money is, we're not going to be able to do this for 8 billion people. If we're going to go down this path and use this plan, it's not going to be for everyone. It's going to be for rich people only. We don't have the time, we don't have the money, we don't have the resources. And so the more influential nations will start throwing their weight around. Maybe required is a significant reduction in societal demand for resources of all kinds. These couple of slides, by the way, raised quite a bit of discussion when I presented this at the IMF. And so we can't change our commodities very easily, and we can't change our technology very easily, but we can change us. So it's implying a radically different system of governance and a very different social contract to what's in place today. And inevitably, this leads to the conclusion that the whole green transition plan in its current form, like it's the only plan we've got. Fossil fuels are going, and this is the only technology we've got, so we are going to do it. It's just not going to work very well. And so it's a stepping stone to something else. It's not the plan. And so it's recommended that we actually give some thought about what that might be. Ecological reality and biophysical limitations will reassert themselves. We need a better plan, something that is actually tethered to reality. So, final slide, tasks to be done. This is every single group I presented to so far has asked, what the hell do we do? And so I've given that some thought, and this is the start. Conduct a Maslow hierarchy of needs analysis loop, not just for society, but for also industry, which allows our society to function at the moment. So from the point of view of industry, what does industry need to survive in terms of hierarchy? What does food production need to survive in context of food? And then go through the hierarchy of society first, industry, food, energy, and you're going to go through a loop again and again, and it'll become apparent if something's not possible, the whole system crashes and you have to go back to the drawing board. Reorganize the industrial value chain around low energy future and the very supply chains that are inconsistent in performance. Retool the existing power grid into a network of microgrids that can transfer power between them and still function if part of the grid is shut down. Each microgrid will support a vital industrial function like a smelter or a social function like a hospital, a school complex. Develop an engineering technology that can cope with variable power supply, variable voltage, variable current, variable frequency, power spikes, brownouts, all of that. If we can have a technology that can cope, then we won't need the buffer. If we don't need the buffer, a lot of our raw material requirements will not be needed. Plan for a reprioritization of industrial capacity. Some industries are about to become a whole lot more important than others. Plan for a systemic merging of energy and raw material feedstock supply with all industrial actions. They are no longer costs of doing business. They are now rate determining steps. Plan for an economy that can periodically shut down, become more in tune with the seasons, shut down over winter, right? Instead of 100% all of the time. Develop an decision-making system that can define whether an industrial outcome is logistically sensible or economically viable to a new set of constraints. Now I'm proposing exergy, an energy term. We also probably need an ecological term in there somehow. Develop the capability to particularly quickly find substitutions for material products or industrial outcomes as the supply becomes non-linear, unreliable, or unavailable. So evaluate what's really needed and plan to do it in a regional scope. We are no longer have the complex 6-continent global supply chain in place. We are now have to develop things regionally. All right, that's it.